Hey everyone, and welcome. Today, we're diving into the really fascinating and honestly sometimes pretty weird world of brain imaging. We're going to find out why some of our most high-tech pictures of the brain look like they've been warped in a funhouse mirror, and more importantly, what scientists are doing to fix it.
So here's our game plan. First, we'll look at the problem itself, this funhouse mirror effect. Then, we'll talk about why it's actually a pretty big risk for science. After that, we'll get into the solution, how to correct the image, the two main ways to do it, how you pick the right tool for the job, and we'll wrap it all up with this ongoing quest for a truly perfect picture of the brain.
All right, let's jump right in. Part 1, the brain's funhouse mirror. We're starting at the very heart of the problem, a weird quirk that affects some of our most important brain scanning techniques.
So, have you ever seen a brain scan and just thought to yourself, wait, that doesn't look right at all? I mean, these images come from these incredible multi-million-dollar machines, but sometimes they come out looking, well, stretched, squished, and just bizarrely warped. And there's a really good reason for that. And you can really see the difference here. On the left, that's what we expect, right? A nice, clean, crisp structural image. But on the right, that's the reality for certain types of scans called echoplanar images, or EPI. You can see them right there. And trust me, that's not what a brain is supposed to look like. And it can get way, way more extreme than that. We're not talking about just a little bit of blurring. The magnetic fields can warp the picture so badly that you get things like stretched eyeballs. It's one of those things that as soon as you see it, you know something has gone seriously wrong with the data.
Okay, so you might be thinking, it looks weird, sure, but is it really a big deal? Well, in part 2, we're going to see why these warped scans are much more than a visual glitch. They're a major threat to getting good science done.
Yeah, this is way more than a cosmetic issue. Think about it. If your picture of the brain is all warped, you can't line it up with a real anatomical map. And if you can't do that, you might come to totally wrong conclusions about brain structure or how it's working. This problem is at its absolute worst near your sinuses, where you have air right next to tissue. That means crucial areas like the temporal lobes and parts of the frontal lobe get hit the hardest. Now, while this distortion messes with a few different kinds of imaging, one of them is the absolute worst offender, diffusion MRI, or DMRI. It's just particularly vulnerable to these little imperfections in the magnetic field that cause all this warping, making its images look, well, terrible.
But of course, you can't have a problem like this in science without people coming up with a solution. So in part 3, let's talk about the clever process designed to rescue all this warped data. And the hero of our story has a bit of a mouthful of a name, susceptibility distortion correction, or SDC for short. The idea behind it is actually pretty brilliant. You take some extra calibration pictures while you're at the scanner, and then you use those pictures to run a mathematical process that basically unstretches and unsquishes the image, putting it back into its correct shape. Now, this is where it gets really interesting because there isn't just one way to do this. In part 4, we're going to look at the two main toolkits that scientists use to perform this correction. The first method is called the bipolar approach, and the idea is just fantastic. It's beautifully simple. You purposely take one stretchy picture and one squishy picture, and you use those two opposites to figure out what the true, correct image in the middle should look like.
So here's the first half of that puzzle. This is what's called a blip-up image. It's collected in a way that makes all the distortions stretch outwards. And yep, there are our famous stretchy eyeballs again. And then you do the complete opposite. The person running the scanner acquires a blip-down image. For this one, they flip the magnetic field gradient so the distortion goes in the exact opposite direction. It squishes everything inwards. Finally, this is where the magic happens. A piece of software takes the stretchy image and the squishy image. It basically averages them out, and it calculates the true undistorted shape, and boom, just right. It is such an elegant solution to a really messy problem. So, let's break down our two main methods. We have the papillary method, the stretchy and squishy one we just saw, and then there's another called field map correction. Instead of finding the middle ground, the field map approach creates a direct distortion map of the magnetic field's flaws. As you can see, papillary is really the go-to for that heavily distorted DMRI, while both methods can work for fMRI and ASL. Okay, so if you've got these two different methods, how do you know which tool to use for which job? Well, in part 5, we'll see that it really depends on what kind of brain scan you're trying to fix in the first place. So, which one is best? Well, for DMRI, with all of its really severe distortion, the PeopleR method is pretty much the gold standard. For fMRI, both of them work just fine, but you tend to see field maps used more often.
And for another type of scan called ASL, there isn't really a strong consensus, but experts often lean towards using field maps.
Okay, but hold on a second. This brings us to a huge practical problem. So you've done your main scan and you've collected your special correction images. But how in the world does the processing software know which correction file is meant to fix which brain scan? It's not magic, right?
The answer lies in this tiny but absolutely critical piece of information called the intended for field. It lives inside a little text file that accompanies the scan. The best way to think of it is like a shipping label. It literally points the software to the exact scan that the correction image is supposed to fix. It's the instruction manual.
The crazy thing is, this super important field goes missing all the time. When researchers convert their raw data into a standard format, some of the tools just forget to create it. And what happens then? The correction software is flying blind. It doesn't know what to do, so it might not run at all. This means researchers often have to go back in and add that crucial instruction by hand using other tools.
Okay, let's bring it all home for our final section. It's time to zoom out and recap this whole journey, from a warped funhouse mirror image all the way to a clear, scientifically accurate picture of the brain. So let's put it all together. What have we learned? We started with these wild, distorted brain scans, especially DMRI. We know this warping is a real threat to getting accurate results. But we also know that susceptibility distortion correction, or SDC, is the essential fix. And for that fix to actually work, the data has to be organized perfectly, with that little intended for field acting as the all-important instruction manual.
And all of this leaves us with one last, pretty big question. We're always building more and more powerful MRI scanners so we can see the brain in even greater detail. But the more powerful the scanner, the more complex the distortions they can create. It kind of makes you wonder, are we locked in this perpetual arms race between our imaging tech and our ability to correct the very problems it creates? It's a fascinating challenge in the quest to one day see the brain with perfect clarity.